Okay, hi class. I'm very excited today to have George with us. So George is currently doing his PhD with Hill University, but he's been working for a long time in industry, developing code for many different real-life tools and systems that have actually made an impact on our lives. And some of them, they also made it to Mars. Right? So that has been very interesting. So today he will be talking to us about his latest project on OSDB, where essentially we're bridging some challenges that OS faces with whatever the DB can really help them. All right? And without any further ado, the floor is yours.
Okay, thanks. Morning, I'm Chris in blue, Neville-Neil. So this is research I'm doing with my advisors, Robert Soleil, Avi Silvershot at Yale, and then other graduate student, Stelios Kassididis, and then undergraduate Sean, and Peter Alrose at UC Santa Cruz. So I get to ask questions because it's more of a class than a lecture. So how many people have taken an OS class, an operating system class? Good, most of you. So I don't have to do too much explanation about what the operating system is. But one of the motivations for the work is that here's a very generalized structure of an operating system. And I like to always just say there's all this stuff. So the operating system is responsible for making it possible to run your programs on top of the hardware, right? And it's this layer in between. And the goal of the operating system is to manage the hardware in such a way that everyone gets to use it. And depending on the application, sometimes you get to use it in a fair shared manner, and sometimes you get to use it in a real-time manner where certain things are more important than others. So we're talking about operating systems writ large, every operating system. Most of the operating system is actually here. This is going to be fun. And device driver stuff. So if you look at a modern POSIX system like a Linux or a FreeBSD, 90% of the code is all the device drivers. And for those of you who took an OS class, all those cool things you learned about like memory allocation and the scheduler and file system, that's 10% of the code. Most of it's way down here. But in between that is this state that the operating system has to manage in order to manage the hardware and to make it so your programs will run. So I've been an operating systems developer for most of my life, which is a little terrifying and quite long. Okay, so the role of the operating system is to manage the hardware and to make it so your programs can run. Now, as someone who's been doing operating systems most of his life, actually, I don't really care about programs because they're way up here, and I'm much more interested in them down here. But eventually, we do want to run something. So this bit in the middle, the OS state and the stuff that's internal to the operating system, is basically a bunch of data in a very large program that has to be managed. And so one of the things that we thought about, and in particular, Avi Silvershot thought about this in the 80s and did a paper that's now up on archive called ROSI. And so the idea in ROSI was to try and replace the shell with a relational interface. But we went a little further than that. So like I said, the operating system has to manage this internal state and make it available for querying, right? So you have to be able to say things like change the routing table or bring in a network interface up or turn on your video or do all of these other things that you have to tell the operating system to do by talking to the devices. So if you look at an operating system in this way, the operating system acts a lot like a database, but with a lot of ad hoc ways of getting at it. So you have all the config files. In Linux, you have everything in a file system, /proc, /foo, /bar. FreeBSD, you have the sysctl tree where it's like, I change all of the kernel statements, syscontrols. And then you have 500 system calls. So over the 50 plus years that POSIX-like operating systems have been developed, every time we need a new feature, we add another system call, which is how you wind up with 500 of them, which is not a really great way of doing things. And we don't version them, so we just keep adding more. That's why you get things like, with 2 at the end. So you have this ad hoc, non-relational way of getting at this state. And so could we do something better? So here's a very simple example. How many people took a networking class? Well, many of you could. I now have faith that I will not die because someone didn't know about networking operating systems when I'm in a hospital on an embedded system hooked up to the wall. That's my biggest fear. It's like, it's either gonna be my code, and then I'm really gonna be bummed, or it's gonna be someone who didn't study these topics. So in networking, when you do your first networking programs for a class, the most common error is you ran the thing twice. Right? You're like, I ran it once and I didn't realize it hadn't crashed or hadn't exited, and I run it again, and I get this ridiculous error called e-adder in use, which you then have to go look up. And one of the things that is hard to do because of the history of the development of operating systems is to figure out who owns an open socket. And why is that? Well, the original POSIX-like operating systems, the original Unix, didn't have networking. Networking was added much later. And we all know what happens when the second person comes along on our design and adds something else. They don't always quite match up. And so this is true of almost every new feature in the operating system. So the original stuff that was done by Kernighan and Ritchie in Unix, which is a file system that we don't use anymore, and a scheduler and memory allocator, that stuff all kind of hung together because a small team worked on it. But then over time, Sam Leffler did the networking stack. He did an amazing job, but it wasn't the same. There's been multiple new file systems, and then Linus came around and made a clone of Unix because nobody has a new idea anymore. And then every single feature has this effect where the person who built it was like, I need some sort of data structure for this. And they didn't look at the data structures that came before. In fact, there have been, if you look at something like a BSD, which has been running for 40 something years of development, you'll see these periods where someone finally comes in and says, why are there 5 different memory allocators in the kernel? Right? This is a thing that was there. It's like, oh, there's a memory allocator for the file system. There's one for the buffers. There's one for the network stack. And they're all different. Why? Well, because over 10 years, 5 graduate students came through, and that was their PhD project, and then they left. And behind them, they left data structures and memory allocators. So one of the reasons that this is hard to do isn't that it's intellectually difficult. It's just that whoever left this behind didn't make them match each other. And the other thing that's, of course, a challenge in operating systems is as they've grown larger, you can't hold this whole thing in your head. So the NSA famously for many years only used version 6 of Unix. And like not like Linux version 6, like version 6 from like when I was 5 or 7, a long time ago. Why? Because one person could read the code and understand the entire operating system and analyze it and know whether or not it was secure. That's their end. There are 20 million lines of code in FreeBSD, and there are 40 million lines of code in Linux based on the number of device drivers they've added. I defy anyone to understand a tenth of that, right? And so you have this problem where as things have grown, one person doesn't know where all the things are. And so it's quite natural for someone to add a feature and not realize, oh, by the way, Bob or Alice 10 years ago did a thing that you might want to use that has like half of what you want. But they're like, oh, I didn't know about that. Well, now you have this new thing, and they don't relate to each other. So this brings us back to e-adder in use. Why can't we just find this? Well, first of all, we have the problem of an accretion of things over 50 years. So what program do you even use? And how do you find the right output, the right command line? And how do you find the right arguments? I mean, now if you're over 35, you would use Stack Overflow. And if you're under 35, you'd use ChatGPT. People used to use Google. But you have all of these things that have come up over time. So like even on a Unix system, PSAUX minus EF, right? Which is, first of all, what does PS even mean? Does anyone know what PS means? Yes?
PowerShell.
No. I do like that guess. PS stands for process status. Because, 50 years ago, someone was like, oh, let's call it PS. And also 50 years ago, you had a teletype and it was really hard to type. So everything is super short. And I think Kernighan said if he had been able to do it again, what would he change in Unix? And he said he would have put E on the end of create in the system called, because it's create. I think is pretty amusing. Is like, that's the only thing you change? Anyway, so you don't really know how to find the right commands or what the options are. So that's a difficult problem. And so for people who work on databases, you think, well, wait, but there's like this set of relations, but not in the operating system, at least not yet. And then the other problem is the output of, in particular, Unix-like operating systems or POSIX-like operating systems is mostly unstructured text, right? So what was the key innovation in Unix? They went from systems that were difficult to port, written mostly in assembly language, which, you know, I like assembly, but anyway, written mostly in assembly language, which all had differing types of data structures. So like in old mainframe systems, when you opened a database, you had to know that that database stored its structures in a particular way. And actually, before databases was the whole the file structures thing. If you want to see what databases were before, that's an interesting bit of history. But in Unix, everything's a byte stream, right? So great, we don't have to know anything. We just open a file and we read bytes. But what do those bytes mean? Well, that's up to you. Good luck. And so this is the output of a couple of the commands we would normally use to try and correlate this data. PS is on the bottom left, and netstat, which shows us the statistics for the network sockets, is on the upper right. And you might notice, if you can read this, which maybe you can, you're young, you should be able to read this. There's no process ID or anything in the network output. There are process IDs on the left. So there's this key you might want to correlate on, but there's nothing there. And you have to basically write some form of script, Python, shell, awk, to try and correlate this data. People have done this a million times, usually badly. So you lack this ability to do joins, right? Joins are super powerful. We would love to be able to do that. And then you have this other issue. So why has no one ever put a database inside an operating system kernel? So forever, and you can find, like, there's a famous paper from Stonebreaker back in the 80s where he talked about why he doesn't want to use the operating system. And now there's this word that he's been pushing called DBOS, where it's like, we're going to get rid of operating systems. We're just going to do everything in the database. And you're like, Mike, you're using a ton of Linux code, so clearly you're not getting away from the operating system. But there's this tension between the two communities because of how we design our software. So database people have, they start with their constraints. They're like, this is how we're going to build the database so that it satisfies these constraints. And we've got COD logic and some really nice things. You have nice things. Operating systems people, we don't have nice things. So database design is top-down design, starting from the constraints. And there's this really nice thing which I learned about by doing this work. So remember, I'm an OS person, not a database person. A database can stop time. You can stop. You don't want to because the performance will be awful, but you will not break the correctness of the database if you stop and do something, right? Like deal with a lock or something like that. And you have this cool thing, optimistic concurrency control, which we don't normally use in the kernel. Operating systems are built down, bottom up. Literally, good luck with that hardware. I mean, many of the things that I have done in my career prior to going back into academia is literally being given a brand new board and told, okay, so make our operating system run on this. Like, can I have the manual? Sometimes you have the manual, sometimes you don't. And so from an operating system design standpoint, you're trying desperately to make this hardware look like the other hardware you've used before so the applications can still run on it, which is why if you look at modern operating systems, they actually all look like they run on a PDP-11 because that's what Unix was written for. So they think about rotational latency on disks, which doesn't exist anymore. They think about devices we don't have anymore. They don't understand new devices. And so people do all this crazy stuff to get around it. The other fun thing, so now if you're building a database like an Oracle database where it runs directly on the hardware, you have the OS problem too. But if you're running MySQL in an application, you don't have this issue. Postgres, wherever, SQLite. Asynchrony. So when a timer goes off in a piece of hardware, the operating system can't ignore it. It can't be like, oh, that's a bummer that went by. And so there are these events that we don't know. I mean, timer, at least you could probably predict, hopefully. But you don't know when they're going to go off. You don't know when a packet will show up. You ask, especially in the old days, when you asked a rotating disk for a block, you didn't know when the block was going to come back. You were like, hey, go get me block number foo of this data. And 9 milliseconds later, there'd be an interrupt. You're like, the block's ready. And the operating system couldn't go, oh, I'm sorry, I missed that, right? And so we had this asynchrony issue that we had to deal with in operating systems. And these are sort of some of the reasons why these two worlds have not normally overlapped. Looking at the history, which I've had to do for the paper we wrote, people have put databases right next to operating systems. System 38 did this. There was a system, oh my God. The original name is like totally inappropriate, so I have to remember the better name, PIC. The PIC operating system, go look what it was called earlier in 1965, because I'm really like, the DEI people will shoot me. But it was the 60s. PIC was a bit like having a database in an operating system, but it was more, they just wanted better access. And this is the argument that's been made before, like every database person says they don't want the buffer cache. So the buffer cache is a thing in the operating system, especially in general purpose operating systems, where you've asked for a block from disk and we put it in memory. And we want to maintain this cache in memory because that's fast. And we don't want to keep asking the disk for stuff. But to a database person, they're like, no. First of all, I probably won't reuse the block, A. And B, I care more about durability, right? I want the thing to be on disk. And if the operating system is hiding things in this buffer cache, I don't have control. It's a very common tension between database and OSP. So for these reasons, this kind of thing has it's never been done in production. Except in one embedded system, which is unfortunately proprietary and I can't get at the source code anymore. Someone did it was kind of cool. There's a company called Routerware, and they did, using an embedded system, basically a software-based router when that was still fast enough. And they started from the data. They didn't start from the code. And so everything was in the database. Every piece of configuration data, everything about the system was in a database, little embedded database. Super cool. And then they got bought by a company I worked for, and that company got bought, and that code is now no more, which is why open source is so much better. So we have this natural tension. Questions, since I talk a lot. Cool. So let's talk about the big structure. Wow, that doesn't blow up very well. That's the one ring. I mean, if it was really the one ring, that would be super cool, because then I could do super terrible stuff. But it's a picture of the one ring. So in Unix-like operating systems, everything goes in the process, because basically every program is a process. And so every new feature that's ever been added to any Linux, BSD, whatever, and iOS is a BSD thing, so it's macOS, is just another field in a C structure. Currently, that C structure is 110 lines long. There are 110 things in the process structure, which is why it's the one ring. It's also utterly ridiculous, but I'm not going to get into that because that's OS design and not database design. So let's talk a little bit about the process table. We'll talk a lot about it because it's this very central data structure, but there's a bunch of other data structures that are important. So to give you an appreciation of how awful this is, don't read this. I mean, you could if you want, but this is the first 24 lines of 110 lines of stuff. And actually, this is FreeBSD. To our credit, I would like to say, to our eternal credit, the comments actually reflect the locking, right? So in a multi-process, multi-core system, you have to lock a whole bunch of this stuff. And so these little letters here, which I'm not going to explain, talk about who gets to lock this when, right? It's super complicated. It's incredibly painful. But this is the central data structure for a POSIX system. So it's one of the things we want to be able to expose, especially since we're going to correlate almost everything else in the system to it. In particular, when we're talking about telemetry, getting data out of the kernel. Most of what a person wants to know is, how does my program relate to some other part of the system? And so this becomes a very central data structure. Okay, so now I'm going to do the risky live demo because I'm an idiot. First, I'm going to make this very, very large. I will share it in a second. Okay. I'll stop sharing just that. And then share terminal. Yeah. Oh, it's big. Good. Oh, I cheated. So this is, go back. So I talked about wanting a relational system, but also we talked about the fact that it's really hard to figure out how to know something about the kernel, right? Because I have to know, well, PS is processes and netstat is networking, and there's like several hundred commands that have been written over, and they all sit in like slash bin and user bands. So in a database system, one of the things we can do is we can say to the database, tell me what tables you have, which is this. These are all of the tables. This is the first set of tables we did for the paper. The paper is insider of this. And we felt that, well, the US guy was like, well, if you want a bunch of tables, why don't we have these? And so we have two sets, ignore all at the top. So processes, threads, TCP sockets, UDP sockets, files, vnodes and inodes are file system objects. So an inode describes a block on disk. Like when you have a file full of stuff, every block has an inode. It's a physical thing. A vnode is a virtual node. It can describe anything in the system. They usually wrap things like sockets or files or other stuff. Directory entries and then NSF clients. NFS clients. There is no more NSF, so it's fine. So they're not NFS clients. NFS clients, because it's another interesting thing to look at. And you can see what we did for done enough databases, then you know this, that the real tables are at the top, and then we have these views. The views give you the most recent data. But one of the things we implemented was snapshots, right? So we can time travel. I can periodically collect data about some structure and then time travel, and I can join it. But back to the original reason why we think that this interface is a good interface, now I can explore the system, and now everything is regular, right? I can find out what it has, and I'm going to cheat and say, hey, tell me about TCP sockets, and I can find out what the data types are, and these are all database data types. These are not what you would get in the C code. So to someone who does networking, this makes perfect sense, but I'll tell you a little bit about it. Local address, local port, foreign address, foreign port. This is what describes every socket connection in the internet, right? It's the 5-tuple effectively. Flag, state, we care about this for TCP, like, are you connected? Are you trying to connect? Are you trying to wait for the maximum segment length until things end? And then we've got a couple of things to measure performance. The smoothed round trip time. For those of you who took a networking class and looked at TCP, you would know what that is. If you don't worry about it. You can look it up later. And then the other thing to note is that every single table has a timestamp. And the timestamp is just that I don't know that this is the right term because I'm still an OS person. I consider it a synthetic column. Like we create that column every time we take a snapshot. And what I've realized, and we're going to see how far I get with that chunk of research, is, everyone's trying to find the primary keys of things when they want tables. Like, well, how do I relate this to that? And we have some obvious ones, like the process ID is the primary key in the process table, the thread ID in the thread table. For a socket, it's actually a combination of columns. But really, if you're doing telemetry, the thing you really care about is the timestamp, right? Especially on a local system. Now, once you get to distributed systems, then you get lamp port clocks and your life is difficult. But on a system where all the course clocks are synchronized, which is a modern system, then coming out of the kernel, all your timestamps are the same. They're all monotonic, which means that things that you may really want to correlate on, especially for telemetry, are the timestamps. Like, tell me when these two things changed. When did this counter go up? When did this thing fail? And you also care about other stuff like, oh, the memory's only going up. But as a column to correlate on between multiple tables, the timestamp is probably the thing, or as I like to say, time is of the essence. So we can do that, and then we can just look at the tables. So OSDB, there we go. So I can just say, show me all the processes, right? And then, okay, the timestamp is a date minus R. For those of you who know what that is, you can look it up later. I don't print it out as a string, but I've spent my life looking at these numbers, so I know what they mean. This simple thing, and so now we can get this out. And then we have more complicated queries that I'll talk about in the slides. But this is all here. I'll show it's not a fake demo. This is a FreeBSD box. It was built this month. That's right. We built the kernel recently. Running our code. This is in a VM on a ARM system. Questions other than why on earth would you do And I will now stop the risky demo. My fault. All right, so this was in case the demo didn't work. Look, okay, demo. So we want a relational interface. Why? Because then we get the standardized query language, which, you know, is the COBOL of data analysis, but it still works. It's not very pretty. I mean, as someone who programs in C, I'm not really allowed to cast dispersions on other people's languages. But it allows us this incremental exploration that we looked at in the demo. I can go through and say, tell me about your tables. Tell me what tables you have. Tell me the schema. Oh, tell me what the primary key is. But there's something else, a couple of other things that are really cool. We talked about joins. I'll show some actual joins in the slides. But one of the things we realized is, or I realized as I was doing the work, was that it also preserves the native structure of the data. So I said that all of the Unix tools pull all this unstructured text out, and then you have to write scripts to, you know, correlate the data and you know, oh, my field separator is a tab in some cases, which is just awful. But instead, if we're operating inside the program, the kernel is the program, we're operating inside the program. Oh, an int is an int, and a real is a real, and a string is a string, and a pointer is very dangerous. But because we preserve the native structure of the data, we can operate on it. And I'll talk about this towards the end of the presentation. It's more efficient, right? Instead of turning everything that was a number into a string, bringing it into, copying it into user space, which is expensive, and then running another program over it to understand what it did and then spit something out, we can go to the source of the data and be like, tell me what that is and add that to the other one and give me an answer. And that's actually far more efficient. So for all of these reasons, we want a relational interface, and that's what we have. We've got SQL queries go in and relations and data comes out, and the work is done down where the data is. How do we do this? And in particular, this is a really important point for the research. How do we do this incrementally? So I would be perfectly happy if someone dumped $1 billion on my head and said, hire a team and for the rest of your life, write a brand new operating system from scratch. Like, I would come to work every day on my bicycle and I'd be very happy. Nobody is going to do that. So we have to take existing systems and change them incrementally. And that's really important. The big bang thing is not going to happen, or is unlikely to happen. And then how do we model the kernel state incrementally? Like, even if I don't write a new operating system, there are 190 potential tables in the kernel. In fact, one of Alex, who was on the initial slide, one of our undergraduates, wrote some code. He and Brian Choi wrote code to structurally go through the kernel and look for all of these data structures that would be potential tables that we should extract. And so automatically extract the structure. And you're like, oh, that's going to take a long time. So you have to pick and choose, right? And as you saw, we picked and chose 7 tables for the initial work. And then we have the other fun part, which people who take database classes get to learn about, which is how do we maintain correctness in the face of concurrency and asynchrony? The second part being the hardest part. So took an incremental approach. We did not rewrite the entire 20 million lines of code from scratch because I'm not going to live that long. Nobody is. And then we put a query processor, we put SQLite 3, which is an open source database that's very embeddable into the OS kernel. And in fact, it had actually been put into the real-time kernel that I worked on a million years ago, which is the one running on Mars. There's a VxWorks version of so it's a well-known embedded system. So we just ported it into we took a couple months, we ported it into the kernel. And then we use the existing data structures as tables. I'll talk about why we do that in a moment. And this gives us the benefits of a relational OS in a pay-as-you-go fashion. And we call this approach the ship of Theseus. Luckily, the professor knows all about Theseus because it's a Greek myth, in which the ship was brought back after the Peloponnesian War, one of the wars, and as a trophy. But, you know, ships are made of wood. So every time a piece of wood would rot, they would replace the piece of wood. And if you replace all the pieces of wood, it's the ship of Theseus. And this is, I'm told, a deep philosophical problem and the reason that transporters kill you, because it turns all your atoms into, anyway. Ship of Theseus. If we replace every table in the kernel with another table, then is it the same kernel? And how many angels can dance on the head of a pin? All right, so modeling kernel data. So why is this a tractable problem? It turns out that C is a really dumb language. C is basically assembly language with for loops and has no data structures. Like you can have an int, you can have a real, you can have a pointer. That's it. And so especially for systems code, when we build data structures, I keep putting scare quotes up, it's just a list of C structs. We have a bunch of list macros. In fact, for FreeBSD, all of the list macros for queues, lists, not hash tables, but everything but that is in one file, q.h. So a bunch of macros, and that's why Alex and Brian's extractor code could go find most of them. And so you get this thing where in the OS, you have a list of C structs. Oh, well, that's a table. Each C struct is a row, each field is a column, and kernel addresses can act as foreign keys, right? So as you saw in that little bit of struct proc that I abused you with, there's all these pointers that are like, oh, I'm pointing to the thread table, and I'm pointing to my children, and I'm pointing to this. Those can possibly be potential foreign keys. We have to actually do some analysis to find out if they're appropriate foreign keys. But that's what makes this problem tractable. If you had like 50 types of data structures, it would be even harder. But the only people who do that are way up in user space, and you're above my pay grade. And then we have this issue of correctness. How do we deal with query semantics? Especially, so for telemetry, it's fine. Certain people would argue with me. For telemetry, it's not so bad. Right? I'm not making a change to the table. Just tell me about yourself. And so if the data is a little late or the timestamps are a little off because this came first and the snapshot came second, that's not great. You want the highest fidelity data you can possibly get. It means you want low latency and all that other stuff, but it's not going to crash the kernel. But in our system, we want to be able to make updates. And that's when the real fun begins, because now we're trying to say to the operating system kernel, oh, by the way, go and make this change to your internal state. And inside the operating system, we already have like a whole bunch of locking issues. We can't hold the locks during query execution. So what we do is we actually we don't want to create a new set of locks. We actually reuse the existing kernel locks. So since the advent of commodity SMP hardware, which is about 2002, people who work on system software have attempted to make their software multi-threaded because otherwise it does not perform well. And so for FreeBSD, Linux, et cetera, everyone has a multi-threaded kernel, but that means you have all of this locking stuff. And we don't want to add another one because we're not going to get it right. It's going to take forever. So we reuse the kernel locks, and then we do this two-phase locking. We acquire all the locks we need. We make a memory-to-memory copy. We call it a snapshot. We release the locks, and then we execute the query on the copy. And we get these snapshots that are transactionally consistent time series. Why does this work at all? Well, in database terms, the amount of data in the kernel is small. Like it's not gigabytes. It's not even, I am hoping it's not a megabyte, but I don't want to say that. It's probably not even a megabyte. It's very small. 6,000 processes in a process table is still, that actually might be 6 meg. But compared to like database writ large, not really a problem. And then we execute this on the copy. So this is the read-only query semantics. This is before we do update. So here's the fun part. So first of all, what does an update even mean? Like when I call update in a database and I say, oh, update Bob's salary to, 50,000 from 48,000 or wherever it is. That's a very tractable sort of like databasey problem. People think about that when they're thinking about database design. But, I'm going to make an update in the kernel. What am I going to do? And so we have to decide table by table, column by column, what's appropriate. Because we don't want an update to do something like the first one. If I change the process anyone can change the process ID of a running process, then you can have two processes with the same process ID, and then you have a confused deputy, which is a security problem. You ruin the consistency of the kernel, right? The kernel will either crash or you'll get that out of it. So we have to say what an update means in all of these ways. And this is another one of the things where it's not amenable to AI. Let's put it that way. Someone who designed the operating system has to be like, oh, that would be bad. That would be good, or that would be okay. Most people never say it would be good. We're like, bad, not bad. But for instance, you could move a thread around. You could say that this thread should be running on core 6 instead of core 5 for performance reasons, whatever, that's perfectly reasonable. So we define the update, insert, and delete semantics for the database on a case-by-case basis. We made everything read-only to start because that's the only way to not lose your mind. And we make sure that things don't corrupt kernel state, and we reuse the existing kernel APIs. So what do I mean by that? One of the updates you can do is you can kill a process. So there's a program called kill, user space, program that you see something running away on a system, you're like, oh, kill that program. But that's based on a system call that eventually goes into the kernel and calls something called kill. So kill in the operating system kernel, that pre-existing function does all the locking. It knows about the process table. It knows what it has to recycle, and it knows which locks to take in which order. I don't want to do that twice, right? And so what we do is when you do an update that will kill a process, and we have that ability now, when it actually gets into the kernel, it does the optimistic concurrency control, which we'll talk about in the next slide, and then it calls the kernel's function. I did not write a new kill function. I do not want to write any new kernel code to make this work, if I can help it. So I talked about stopping time, right? So we can't stop time. Things happen asynchronously. You just can't do it. So we picked a typical optimistic concurrency control, which is calculate a digest over the table, compute the effects, calculate the digest again, and then if the digests are the same, commit or abort. This is complicated by the way operating systems work. So some state in the operating system changes all the time, like counters. So how many packets arrive? Like you're not going to be like, oh, well, in 10 seconds, the packet number, or in a second, the packet number is going to change. Or blocks read, or CPU cycles used. Every single bit of those things is going to change constantly and can change asynchronously. So we actually look at the tables we have column by column, and we treat that kind of data as volatile. That's the term we used for it. Slightly confusing to C programmers, but I'll put that alone. We have a volatile data type. So treat this data as volatile, and then we ignore it in the digest computation. We decide that it is not important for us to worry about that in an update. Now, there's a problem here, right? So it could be, in the case where I'm talking about moving a program for performance between two cores, that you would crash your performance because you would bounce it back and forth as the numbers keep changing because you're ignoring those changes. So there are definitely downsides. Like there are problems with this. But as far as we can tell, and we'll see how we get on with the research, it will not break correctness, right? It will not cause the kernel state to be incorrect, because that's like a little red light comes on and the kernel reboots. You're sitting there on United Airlines watching your screen reboot, I mean, reboot your seat, sir. I never thought I'd live long enough to hear those words. So it won't cause a reboot. It won't cause inconsistencies, but it could still cause these perverse performance problems. That's the only solution we've come up with so far. So let's go all the way back. I asked you how you'd find the port. Now, this is a database class, so maybe you think this is a really beautiful piece of SQL. I look at this and I'm like, my eyes hurt. So this is how we do this. This is a join using standard SQL for SQLite 3. And this gets pumped into the kernel, and the kernel comes back and it tells us who's sitting on what. And so, we've got multiple tables. The T is the TCP table, the P is the process table, and then F is files, so open files. And we correlate all of these using a join. And this will spit out the answers. Like this thing is waiting on, these two things are waiting on this, or this one is waiting on this. Now there are programs in particular Linux has one that will actually just spit this out. Someone was like, oh, this is terrible. But then they had to go write a bunch of code. So once you've put this kind of system in the kernel, we no longer have to write new tools that way. We don't have to write another C program that sucks a bunch of system calls data into user space. I can just go directly to the kernel and say, this table and this table and this table that you've never correlated, correlate them for me. and we'll just do that. So we're systems people, which means that all papers must have a performance section. Even, can I say? So how do we evaluate this thing? Well, first of all, what are the new things we can see and do? We talked about that a little bit already. But then we care about things like snapshotting. Like, how much does it cost to copy all this memory? I said that that memory was small in database time, but OS people are incredibly parsimonious. And like, if you look at OS code, you'll be like, wow, you wanted to shave a byte. You realize the machines are 96 gigabyte, never mind. So really parsimonious. They really care about how much memory is used. They really care about how long something takes. So we looked at both the overhead of calculating, getting snapshots, but also we wanted to compare how well some of our queries worked to standard Unix tooling, and we did that. So novel correlation, here's a cool thing we could do. This is straight out of my experience on Wall Street. So when you do high performance code especially in live trading, you are extremely careful about where every program sits on every computer. You have a 72 core machine. I've allocated 70 cores to trading programs. Nobody's going to move for the 8 hours or 7 hours of trading during the day. And that's how you get the maximum performance. You don't trash your cache, blah, blah. And then every once in a while, someone in the ops team accidentally fat fingers one of your programs onto someone else's program. And there's no error, except that the tail latency just goes like this. And then if you've ever worked in a trading environment, people like to yell. My voice is quiet. Just put that up. So you've got an ops guy standing over you going, why is this broken in the middle of a trading day? Not a good moment. So it would be really nice to fix this. And the way that people used to fix this, or still fix this because we haven't shipped the code yet, is really arduous. So usually it's a bunch of scripts. Like, this happens once, and then one of the ops people is like, oh, I'm going to write a program. I'm going to write a Perl script or a Python script or whatever, a shell script to do this. But there's this other challenge here, which is if you've trashed the performance of something on the system, then trying to get the operating system to respond is hard because the operating system is now super busy. And you're like, hey, can you help me do this? Like, you're sending system calls, and the kernel's like, wait, bad things are happening. And so it's never fun. But because we put this little bit of code in the kernel, now we can do this with a single command. And as long as that one command gets past the system call interface into the kernel is now bound and required to execute it for you. So we were able to do this as a little test. So I'm normally a networking person, since I don't know how file systems work, thankfully. So our test is a network test. iPerf is a very common benchmark for networking. It's not great, but it's pretty common. So what we do is we put a couple of iPerf processes, and we specifically did the wrong thing. We put them on the same core. And then we looked at the jitter, which is sort of the best way to find out what's going on, because I wasn't calculating tail latency. And you can see here that, I start one, the jitter goes up, and then I start another, jitter gets worse. And then we hit the process with this piece of SQL. And here you see one of the updates that we talked about. So we can update the threads and we used, we did something sneaky. I used a column called last CPU to sneakily say, oh, someone said change the last CPU. Well, okay, move these two things to two different places. And though the SQL is SQL, under the hood, it's all using the kernel's native programs. So CPU set is a thing that moves things within the scheduler and moves them between cores. So under the hood, it's using CPU set, but to the person who has to do it, it's SQL. One last thing we did that I'm going to show, we did several days, one of the last thing we talked about. So this is another one of these things of like correlating things people don't correlate. So all operating systems have an out of memory checker. So if someone writes a program that suddenly eats all of the memory on the computer, at some point the kernel will come along and go, and that program goes away and you get your memory back. But we don't have that for any other system, any other component of the system. We don't even have it for CPU utilization. You can eat the CPU and there's nothing in the kernel that will be like, oh, you're too busy, go away. We might schedule you down, but eventually you can overwhelm the computer. And we also don't have it for networking. So it's not uncommon in, CDN environments or in high bandwidth network environments where like some program is basically overutilizing the network. It's either blasting the network with too much data or receiving too much data. The system's gotten too busy. Well, with OSDB, we could actually build in SQL. I don't know one of these updates. This is a delete that says, well, if this process has sent more than this many messages in this time, this is a second. This is one of the nice uses of timestamps. Then just kill the process, right? And you can have that running whenever you want, and that will then make the system behave better. Again, without a system like this, a relational system that's built into the kernel, you have to do this with ad-hoc. And again, this usually happens when the system is super busy. So like trying to get the output of commands while you're doing this is totally not fun. So we added an out-of-network checker as opposed to the one for memory is called OOM, out of memory. So we call this out-of-network OOM. Okay, how much does it cost? So surprisingly, probably not supposed to say this on camera. Surprisingly, it doesn't cost that much. When we originally started thinking about this, all I could think were two things. We're going to put a reasonably complex little database inside an operating system, which seems painful. And then, oh my God, how much is this going to like kill the overhead, kill the overhead of the system? Well, you can see, so this is on a 72 core machine. So there's a benchmark called Unix Bench. It's older than everyone but two people in the room. It's from the 80s. It is still the common benchmark of Unix systems, unfortunately. So we ran this, and what we did was we tried to increase our snapshot sampling frequency and then see what happened to the benchmark. And the thing to note isn't the absolute number, it's the changes in height, right? So there's very little change. We have an industry partner in Network Appliance who's working with us on this research now because they are going to try and use it in their systems. And they've done this in a high performance test lab, and they also find very little overhead, which is why they're willing to use it. And then this last thing. So this was super surprising to me because I just wasn't thinking it through, I guess. So we wanted to compare a typical Unix command to what we do in OSDB, right? So PS is the thing that spits out process status. And in OSDB, you saw that select star from procs, right? And so we could construct a SQL line that gave us the exact same output, ordered in the exact same way that PS would give us. We compared this, and what we did was we started and paused 6, 7, almost 8,000 processes. They're not doing anything. They're not using any CPU time. They're just sitting there. But that makes the process table grow. And we're like, oh, well, how long does it take to do snapshots or PS of the process table? And so blue is us. In a systems world, I would never show you this graph if our data wasn't better. So you know our data is better. So this is us, the low graph. And red is PS. So why? So we profiled PS when it was doing this. We found it all the time was in QSort. Because what it's doing, we talked about native data types versus pulling strings out of the kernel, is it sucks all these strings out of the kernel and it runs QSort on more and more and more of them. And QSort is O of n squared. And this is kind of O of n squared. Whereas OSDB is sorting using merge sort, O of n log n. But it's also sorting on the primitive types. It's sorting the numbers, which are small, as opposed to the strings, which are ever growing. It's bad to say that it's surprising about your own research, but it was.
What is the order?
The ordering is it's ordered by PID.
Oh.
Yeah, it sorts on the PID. Yeah, so I don't know. This is a really surprising, but it's a good graph. So, in conclusion, we think a relational interface benefits the OS, and in fact, the standardized interface is nice, but the join is what really sold me on it. Like, oh, okay, I can now really do interesting telemetry that I could not do with the same system in production before we did this. And that gives us actually a large and interesting field of research for not just telemetry, but for updates, for understanding the operating system itself, which is something people are always trying to do. And now we're looking at it for a lot of different things. So like there's a distributed version at some point. We've got a port to Linux. There's a lot of things we're looking at to try and broaden what we're doing with it. But it gives us a lot of power. And let's see, I think I've got some teasers. Oh, if you really want to hear me talk more, if you scan this, you get 8 more minutes of my voice, which is the demo of going through all of this stuff. It's the live demo or the video demo of this. If you have questions, you're interested in the research, you're interested in what we did, email me. I am GNN everywhere, so for Yale, maybe to have a little number. But the CS department gave me my real login, so that's what I use. We're going to put it up on GitHub. We've got the Linux port now, and we're looking at doing things with EBF and dtrace. We think that's a really interesting place to go with this stuff. Questions? And that's the last slide, and we've got 15 minutes for questions.
Let's take those here. Any questions?
Yeah, you said you implemented it piece by piece, so there might be some tables at some point that you didn't have any relational model on top of, and some that you did.
And that's currently the case. So currently, there's in the main branch. Sorry, GitHub. In the main branch, the current ones are the ones that you saw in the demos. I can never remember if it's currently 7 or 8. But there, like I said, there's 190 potential tables. Many of those. This is one of the other things where people were like, you were like, well, why don't we look at it with AI? I'm like, sure, but only one person in the team knows whether that table means anything, and it's me. And a lot of the tables are things that are being extracted from data from device drivers. Now, certain device driver tables you might want, but certain ones you're like, there's no. I mean, we could expose them. There's probably no reason, and we'll still go through incremental.
Are there any problems that are caused if you try to query something that requires some information that has a model on top of it and some that doesn't?
Some that has a what on top?
So if I want to query information, like a join, where some of the information has a corresponding table that you've added in, and some of it does not, does that cause problems? Is it possible?
No, because the way that we've done it is the only thing you can query are the things that we expose. So all the data structures are there, and then we snapshot certain ones. But you currently, that would be interesting. I could break something that way. There could be a challenge if I were to try and run dtrace on this at the same time, right? Because I get for eBPF. Previously we used dtrace, but any sort of tracing system or debugging while this was running, you would possibly have issues. But what you get is incorrect or out of date data, because we do currently still grab all the locks. Like we're like, oh, there's 7 tables, we're gonna grab all the 7 locks, copy, release the locks, and then only work on that. So what would happen is if you tried to run the 2 things at the same time, you'd get one or the other first. You'd get the dtrace output first, or you'd get our output first, and then they'd be offset in time, because when we lock, it can't get any, dtrace couldn't get any either, some other component couldn't get any.
So I feel like this would be kind of a hard experiment to show and prove, but in relation to querying tables and out of date data, do you ever experience OSDB essentially querying data and returning things that are a little bit too far behind in comparison to some of the other bread and butter tools that we use in Linux?
So that's actually a really good question. We have not done the comparison of OSDB to a bunch of tools yet. And so the research we're going to be doing with I'm sure that's going to come up, because they're super interested in telemetry.
Right.
Their current systems are not, they want to get higher fidelity, and they're not close to this fidelity yet. So we'll see what happens. Once we give them this, they'll have a much higher fidelity, and then we'll do the comparison. It's an interesting question, and it's something we should and will look at, but we haven't done that experiment.
Nobody else has raised.
I'll keep saying any questions, but go ahead.
So I know you mentioned that like you want to essentially reuse as many kernel like what is it?
Functions or APIs,
Yeah, APIs like kill, right? But I don't know if you alluded to this or not, but like have you had to essentially rewrite something at any point yet?
No, because we haven't had to rewrite anything yet because the number of updates we do is fairly small.
Gotcha. Okay.
Right. I think that if we were to do something like update an element of a table like the routing table or a firewall table, but even there are reasonable, well, maybe not reasonable, but there's like a known API. I think the really interesting part, though I don't want to do it yet, will be when we start looking at devices, right? Because devices have a whole bunch of, like, there's not just the locks in the operating system. It's like, oh, well, this is read clear. Like, how many people have ever dealt with actual hardware? Okay, so he and I have scars, and the rest of you are luckily angelic in some way. Unsullied. We're all unsullied.
So I think it's related to that. So and the last question, like question about APIs. So it seems that okay, there's specific attributes that if you change, then it makes sense that you call a specific command that. So I guess, have you systematized which attributes are changeable in the approach? Now, I was just thinking as you were speaking that you could say something like, in my snapshot, I can mark mutable attributes specifically, and then with every attribute, I can say, if you mutate this, you're gonna call this function. Like, are you doing something like that? Is it like? So
we do, but that is very C programmer. C, like, it's literally like one of us was like, oh, that one's okay. So in SQLite virtual tables, which is what we're using to do this, you intercept almost every function that the database would do. So like updates come through a function. Right. And so like in the process table code, in our proc table managing code, when update gets fired, I can be like, oh, if you said, and I'm doing the logic. There's nothing automatic about it.
So what I'm thinking is
like to.
Sorry.
You keep going.
So what I'm thinking is that, I mean, maybe this can be a new feature for SQLite or whatever other system, right? That you say, I have mutable attributes and immutable attributes in my snapshots, because that's the whole point. Yeah. And then I have a specific UDF that I call if this is mutated. Mm-hmm. So you can make this a feature of the system, mm-hmm. right? Rather than a one-off. Yep. And then related to that, so you have snapshots, so you don't really operate on necessarily the latest data anytime mm-hmm. you have a snapshot. Yep. So if you try to delete a process, right, or move a process between cores, these examples that you gave us, and you have and your snapshot is it's the most recent, but it's out of date. So what's going to happen? So could we break the system like that? No, thankfully not. So OS programmers are super paranoid. Good OS programmers are super paranoid. So any kernel function, like if let's say the snapshot is out of date and I say kill this PID and that PID is dead. Even if I'm calling the direct kernel function, that function says, PID is not there. It might return an error, it might just silently be like, bye. And that's true for almost all of the destructive things in the kernel. We've definitely checked first because we wouldn't want to break things. Yeah, and I guess if you really limit what is updatable, then you have to. And that's the other issue. So because the first version of this, the current version we're talking about, was bespoke, right? So a kernel programmer was like, what would I like to know? What can I expose? And what can we get out of this to have a reasonable scientific result for a paper? Much more narrow. So now with the automated extraction that's being worked on now, we can pull out, I think now it's 2/3 of the fields in the proc. So that kind of analysis is way more interesting or painful. It might be the same thing. We're really going to have to think like column by column by column, but attribute by attribute, what we're going to do with it and whether it's mutable or not, how it's mutable. And then you've got the issue, like right now, what is a mutation? I can mutate the table. Like I can mutate it. Like the core thing is super narrow. But let's say I've got so 2/3 of 110 is 60 something, right? 70. So now I've got 60 columns. And if I mutate column 7, I don't even know what it is yet. And column 12, then what? Right. And then, but like now I've got 8 columns that are mutable and can I mutate them at the same time? Can I mutate them in order? What happens? Yeah, all kinds of research. It's pretty fun.
So yeah, that's a big challenge. And until we got to the point of having sort of structural extraction, because I could have gone through and done the but I don't want to. So now that we've got the structural extraction, that's kind of the next, I think that's on my very long to-do list, is that kind of thing.
So if I get right, one of your next main goals is to really, as you told me earlier, get the structure of the dependencies between the calls.
Yep. Yeah. And actually to really, I mean, to me, hope Robert doesn't watch this video. To me, one of the things that's always been fascinating, one of the things I've studied for most of my career is code spelunking. Like, how do you really understand something as large as time? And so this, because like there are static tools, they're not very good. Some of them can give you sort of an image, and some of them, they generate basically what I like to call a hairball graph, because there's so many lines, you just can't read it, that makes no sense. This is another way of understanding that. So with structural extraction and some ability to do like semantics and inference over the attributes, over the columns, I think we'll be able to have an interesting understanding. I think about it a little bit like a data tracing version of dtrace. So dtrace and eBPF are all control flow, and debuggers are all control flow. Like how did I get here? Why am I here? Whereas this is like, here's a snapshot of the program's data. People think of data as the data over here. So I kind of think of this as program metadata. This is the program, the data about the program. And now I can look at this over time, and they're very different angle on the program. So I think it gives us another way of both statically, once we understand the foreign keys and all the relations, like how do things work together? And I think we'll find with the full structural extraction, a whole bunch of things that developers didn't think about. Like I'm really looking forward to being able to do enough structural analysis where I go to a developer meeting with my colleague, like kernel colleagues, and they're like, you know, these three things talk to each other and they're not locked. They're all gonna be like, we hate you. I'm like, yeah, fix it. I think that's gonna be interesting. And also another thing I really want to get to is, so in FreeBSD, we were very good, in my opinion, and quite religious about locking order. There is an entire subsystem called Witness that you can run, you don't run it in production, and it doesn't slow it down too much, which checks all of the locking orders, every single thing that everybody's locked. If we can expose that, that's going to be super interesting, because first of all, no kernel lives without lock order reversals. Like you add a new feature and you're like, oh, hey, you realize, Bob, Alice, you did this thing. I think exposing that's going to be interesting, but all future work. I'm going to the end. Thanks.
Any other questions? All right, let's take our speaker again.